As expected, you both did great.
I'm sorry, I think you had all stars for this.
Yeah, no worries. What's up? So my office hours are until 10, so I start teaching at 10. But if you come back in like at about an hour, I'll come back at 11, then we'll be on break and then probably answer a question if you're still here. Okay, awesome. Thank you. Remind me your name again? Alex. Alex. Thanks, Alex.
Thank you.
I do. Chem 100 intro, and it's full. We have a wait list of about 10 students. So it's 58 students total, if you count the wait list. It's a lot. It's very full. Next year we're offering it 2 different terms to try and spread that out a little bit. But so it's going to take me a while to learn their names. It's a little bit different than this class.
Why did you guys switch surveys?
So this is speculation, but from my time here, typically, whatever room this class was in last year, it gets copied over and put in that same room this year. So for whatever reason, at some point, they had us in that room, and I want to say it was because this room wasn't open yet. They had us in the other room before this room opened a few years ago, and that's just been carried on ever since. So next quarter will also be here in all likelihood, unless there's a conflict. There are a few classrooms that have to be in here, like the geology stuff. And so that could have been one of the, I think that there was a geology class in here last term as well that might have partially overlapped. But anyway, did everybody have a good break? It was good. We were in Minnesota for a good chunk of it. So got to do some pond hockey, which is always fun. Made our own rink and everything. And then it got real cold and too cold to go play hockey. And but it was a lot of fun. You guys do anything fun?
New York was great.
Oh yeah, that's right.
Yeah, it was also freezing. Like it feels colder than here.
I want to say that on the coast it's a damp cold.
Yeah.
And that's, yeah. Good. Taylor, did you have fun? You worked, got a lot of hours. That's rewarding in its own way, though, in a monetary way. All right. We're gonna jump right into, I guess I did post the slides. That's the wrong course. Hang on. And everything's all linked. It should look really familiar. Syllabus is posted here as usual. We're required to post the text right onto Canvas so that auto readers and stuff can get it. But it messes with the form. Oh, sorry, you're not looking at the same screen as me. But I prefer the PDF that I always attach to it as well. Our schedule, as always, is going to be a little bit fluid. This quarter has a decent mixture of paper labs where we're interpreting new data or new instruments. Our first one next week is going to be on mass spectrometry. And then carbon 13 NMR is also going to be a paper lab. But in general, and then your lab final for this one is going to be more like a take-home test, where you'll be planning a synthesis. By the end of this quarter, we'll have covered a good chunk of different functional groups and how to convert back and forth between them. So your lab planning for this class, instead of what is this compound, it's going to be, here's a compound and here's the stock room. What steps would you take to make your product? But it'll be similar. You'll each have a different product. It'll have different steps along the way, but it'll be write out. You basically propose a procedure. Here's my goal, then write out a procedure. And I think what we did last time was solving the synthesis steps, just writing out plan. Was 80% of the points, and then the last 20% of the points was actually writing a procedure for that. Obviously, that's a lot more work. But if you want those extra points at the end, if you're in the spot where you need to get those extra points to get to the A or whatever, that's how you do it. You put in the work to actually write a procedure. But it's a pretty fun project. It's a little bit stressful because you've got to get it right. But it's take-home test. And then the other note on here is just I'm not sure what we're going to do for the lab during midterm week. Might make it a review assignment. If one of these weeks takes longer earlier, then we might do carbon 13 lab there because it's a paper lab, so it's got time for you to also do some studying if you want to do a review. I'm just kind of leaving it open. We'll figure it out what it is, what we're going to do there when we get there. I don't think anything else changes. Our schedule's the same. Our classroom changed, obviously, but our textbook's the same. My office hours are the same. I'm trying to think if there was anything in particular. Oh, we have more holidays this time, but that's not going to affect us because we're Tuesday, Thursday.
Right.
So other than snow days, everything else should work pretty much the same as before. And obviously the schedule will change for snow days as we run into issues. You start UNR on the 21st. Okay.
So they'll do Monday, Wednesday, Friday, but. And I plan on traveling the night before. So in case list. Yeah.
Well, you two are both good at communicating with me, so I'm sure that there are any issues come up. True. Yeah. If we do have if it's a bad travel day, but they don't officially call a snow day, we can do a Zoom lecture. If you two are comfortable with that. Yeah. We've all done Zoom lectures before at this point. So, yeah. And all right, I think that's all for syllabus stuff. Questions about the test or how anything went last?
I looked, but I feel like I understand all of the notes that I was given.
I think it was, from what I remember, it was a couple small things here and there for both of you. You both got in the mid-90s, so there's not a whole lot to correct.
It's the things that I didn't feel strong about. It's like still getting my arrows in the right direction. So.
Yeah. Yeah, you both did well on the NMR one.
I was expecting this to be the thing that interested them.
That one, yeah, ice back. So it should have been. That happens. All right, we'll take a second there. And then when you're ready, let's do some alkene nomenclature because our first unit is going to be, instead of making alkenes with elimination reactions, what happens when we react them.
So we're naming this.
So let's name them. Don't forget your E and your Z, right? That's the wrinkle when it comes to alkenes. Yeah.
Yeah.
Video game Tetris. Who remember that? Because every piece of Tetris is made of 4 blocks.
It's a good way to remember. So. Like the right side versus the left side versus the don't belong.
Correct. So out of these two, which one has a higher priority?
Wait, which, where's?
So basically, we're looking at the alkene. And so look at the left side of the alkene. And there's 2 things attached to it. Which side has priority? The bottom's bigger, right? So higher priority. And on this side, you've got a methyl and an ethyl. The ethyl's going to have priority. So because those are pointed in opposite directions, it's going to be across. So if we're using system trans, we call it trans. It's not Z, it's the other one. E.
I know, I was like, I know it's not. Cause C is the same, exactly, that's what I was doing. Which would mean they're both pointing up.
Z would be, yeah, if we flipped one side of this. So it's a little bit tricky to just say the same side because they're attached to opposite sides of the alkene, but they're pointed towards the same side.
That's the number one.
It's really satisfying to get in.
Especially after break clock. And then we don't have to specify on the next one where the bond is.
It's always between carbon 1 and 2.
Is side priority because. Like,
It's a cycle, so could it be the other way? Not really. Right, your cyclos. They kind of have to be C. Or at least the cyclo group has to be attached to the same side. Just because of geometry, otherwise you get some weird twisted three-dimensional thing. With a lot of strain angle, like it's theoretically possible. Have something that was, let's see, what would it look like?
well, cause you're saying our high priority group to both of them is the. Site.
Yes, but can you really connect? We would have to do some sort of 1, 2, 3, 4, 5, 6. Yeah, it would be really, really tricky. Like basically you can get a trans cycloalkene, but only once you get to like 9 carbons. When you got like 9 carbons, there's enough wiggle room that you can get it twisted around like that, but it's really rare. And so unless you specify otherwise, if it's cycloalkene, always assume that it's going to be 6.
Okay.
If you did want to say Z, you wouldn't be wrong, it would just be redundant.
Wait, so the C or the six?
Remember that terms are mostly interchangeable. The one place that they're not interchangeable is on D. We'll talk about why.
There's no C.
There is no C.
I didn't even question that.
It's because I didn't make these, I just screen grabbed them out of a textbook PDF that had more than this. Breaking the walls, first way to get there. So the basics are straightforward, right? The trick is in assigning priority. So for on carbon 3, you got a hydrogen in a butyl group, so it's easy to say that this is the higher priority.
Yeah.
On this side, chlorine has the higher atomic number. So chlorine is the higher priority. So it would be E again. The reason that this is a good example of the difference between E and Z versus cis and trans is that cis and trans is always referring to the main carbon chain. So the main carbon chain is going in the same direction because that's the main carbon chain and that's the main carbon chain. So this is cis, but it's also E. No, because if you use E, then whoever reads that knows the rules should be able to draw the right structure. You only have to specify both if there was a way it could be different. You need to specify both to avoid ambiguity. So you could, it would be less correct, but I would probably mark it wrong. I don't think I would mark it wrong. If you said cis in this case, as long as you know that cis is referring to the carbon chain versus priority. Priority is a little bit more universal, so I would just get used to using E and Z. We'll still use cis and trans, especially when we talk about rings, to talk about on both the same side of the ring or opposite sides of the ring. It's a convenient descriptor, but when it comes to the names, E and Z is going to be a more universal way to do it.
And then when it's in a cycle, it's assumed it's between carbon 1 and 2.
Correct. Which this one still leaves two ways you can count. So count the way that makes the other number smallest. That's not the stereochemistry that's actually tricky here, right? Because we're always going to assume in Z, so we don't need to specify. But we do have another stereo. We have a chiral carbon, which means we need to worry about R versus S. I need it for R. Yep.
So the R beams coming towards us, so the high beams are away from us. And then the double bond is on the right, so we're gonna go to the right first. So after we're doing this. Yeah. You do R before it's E. You don't need to see.
If you do need to specify both, for whatever, like if we wanted to be overly specific in this case, or if it was a molecule where it wasn't a ring, we need to specify, then you would say something like 3R C or 3R2C. Basically, you just put a number in front of the stereochemistry. Anytime you've got two stereo centers, that's a pretty common way to do it. We see it more with R and S. It's pretty easy to have two chiral carbons in the same molecule.
Right.
And so you'd see something like 3R2S. And we can even, while we're reviewing and talking about stereochemistry, you can even have a molecule where the chiral carbon is not a carbon. It's not a chiral carbon, it's a chiral center. There's the more general way to refer to it. But I don't think we did any of these, so this is actually a good example, something that I missed last time. If we had something like. Because what's the fourth thing attached to that? That's a lone pair, right? So we've got a lone pair into the board, a hydrogen out of the board, and then one in ethyl.
So it's a lower priority than nitrogen.
What's the atomic number of a lone pair? There's no protons, so it's there, right? So lone pair is lowest priority you can. So in this case, it would be 1, 2, 3. So it would be S. And we would name this, we haven't gone over naming amines yet. But if we did, it would be our longest continuous carbon chain is ethane. Drop the E and write amine. And then we say it's methyl ethanamine.
Let me just learn.
The point of this is that what I want you to take away from this, because we'll cover amines more detail later, is that you can have a location on a molecule that's not on a carbon that has a number. So if we wanted to say that this methyl group was attached to nitrogen, we would say that it's N-methyl.
Oh.
So, and then we'd specify that this whole thing is S, N-methylethane.
If it was like a primary CL.
If we had something, yeah, you would do something. So I don't think nitrogen's really the only time we have something like that we're going to cover in this class. Because if we have the other common thing that we have in the middle of them, you can kind of think of this as being in the middle of the carbon chain. The only other thing we have commonly in the middle of the carbon chain is an oxygen. To make an ether or an ester, and those have their own specific way of naming that doesn't require. We're going to use parentheses more in that. So, but more details on that in 3 chapters. When we after the midterm, we'll get to kind of day. I just didn't schedule, but now I'm blanking on it. Later, down the road. All right. So I am recording this. And the camera's decent resolution, so it should be able to capture all of the markers as well. Not as clearly as when I was doing it on the smartboard, but it does a decent job. All right. Let's talk about addition reactions. So this is chapter 7 in the Klein textbook. We'll look at our OpenStax textbook, what chapter it is. I think it's chapter 7 now. Basically, alkenes, when they react, the most common reaction that you get from an alkene is going to be an addition reaction. Right? Pi bonds in general are not very stable. Remember that what makes our bonds stable is when we have good overlap between the orbitals, right? And pi bonds just inherently have less overlap because of their shape. So pi bonds are always going to be less stable than sigma bonds. It's pretty much always more favorable, except for aromaticity, except for benzenes. But it's mostly going to be favorable to have single bonds. So the most common reaction we have with an alkene is an addition reaction, which is the opposite of an elimination. Elimination, we pull stuff off to make an alkene. In addition, we add stuff back in to break the alkene. So if we're, this, the first mechanism that we're gonna look at is an electrophilic addition. What does electrophilic mean?
No, electricity.
Close.
There's all electricity.
What is nucleophilic? Meant what? A nucleophile
It does,
means a nucleophile lights the nucleus.
yes, now.
An electrophile lights electrons. So
Electricity.
it is,
So electrophilic is,
means something that's attracted to electrons. So what part of this molecule has the highest electron density, has the most electrons?
um,
Out of the carbon base.
I didn't understand.
Sorry, this whole thing. Where are the electrons?
Oh. With the vectors. And the double.
There's extra electron density there, right? Because you have 4 electrons between these 2 carbons instead of just 2.
Right, because the line was too extra.
Right. So if we were actually drawing what this looked like, we could have a sigma bond between the 2 carbons. And then our pi bond is going to be above and below that, right? If the hydrogen, if the methyls are sticking into the board and out of the board, our pi bond is here and here. So basically, there's extra electron density in an alkene because we've got these big pi bonds, sort of the clouds of electrons are sort of hanging out near the carbons, but not really making a strong bond. So that's the if that's the electron dense part of the molecule, that's going to be what we would expect an electrophile to attack. Which I misphrased that a little bit. We know it's really the electrons that do the moving, right? From our mechanism work, we always draw our arrows from the electrons towards something else. So if those are the electrons that are going to be reacting, what part of HBr is a pretty simple molecule to draw? What part of the HBr molecule are our electrons going to attack? The electrons are going to go towards the lone pairs. I know it's a little bit weak, but you guys know this. Electrons aren't going to go towards other electrons, right? And what's more electronegative out of the hydrogen and the bromine? So where is the partial negative charge in this molecule? On the bromine. So what are the other electrons going to attack? The hydrogen. Because that's where it's missing electrons. We've got a partial positive here. The electrons are not going to go towards another negative charge. So the electrons are going to come towards the hydrogen, and the bromine gets to keep the extra pair. It's a weird week. I hate starting on Wednesdays because it throws everything. I'm feeling the same ways.
We have lab today? No, it's Tuesday. Lab is Thursday. Wait, today is Thursday.
Right, exactly. Everything's backwards. Lab is Tuesday.
Okay, guys, I'm all mixed up. I think it's
It's okay. We're gonna get through this together. All right. So what is this gonna look like after this step? Pi bond just broke
yeah.
to grab an extra hydrogen. So now we've got one of these carbons grabbed an extra hydrogen, and made a new carbon hydrogen bond, right? So I'm just gonna, they're identical carbons, so I'm just gonna pick one arbitrarily. Now that's all of our, and then for the sake of balancing, we have bromine floating around. That's all the electrons we have. So what does that leave us with on the other carbon? Partial positive?
Carbon's small.
The carbon's positive, but it's full positive. It's missing a pair of electrons. Now I had an extra pair of electrons that it was sharing these pi bonds. Pi bond broke. One of the carbons gets a new sigma bond, the other carbon is SOL. For now. Out of one. So basically, when you go through an addition reaction, when you break an alkene, almost always what's going to happen is you're going to make one carbon happy right off the bat, and the other carbon's not happy. But what do we still have floating around? Bromine. So what's the next logical step? We've got a carbon missing a pair of electrons and a bromine with a negative charge floating around.
Opposites.
So opposites attract. We draw the arrow from the bromide to the carbon because it's always the electrons moving. That gives us our product. So it's the exact opposite of an E1.
Yeah.
Because E1, we had leaving group leaves and then a hydrogen gets picked up, right? In this case, the hydrogen gets added back in and then our nucleophile comes and attaches to the other side. Which of these would we expect to be the slowest step? That's step 2.
And is that with the rate for mixed?
Yes. Step 1 or step 2 going to be slower?
Because it takes more energy to break it.
Yeah, and we're making something that's less stable. Starting with everything has a charge of 0, so everything is relatively stable here. We made something less stable. And then we're making something that's more stable than we started with, right?
So the steps are where the arrows
This is supposed to be a straight arrow, but yes. So step 1 is the purple. Your pi bond breaks, grabs the hydrogen, bromine takes the extra electrons. Step 2 is your bromine attaches to the carbocation. I'm sure you remember that we're picky about arrows. Specifically in this case, it's the curved arrows are showing where the electrons move, and the straight arrows are showing a step. So if we were drawing a potential energy surface here, we started kind of low energy. We went through step 1 and we made something that's less stable than what we started with. Then we went through step 2 and made something more stable than we started with. Because we have all pi bonds now, and pi bonds are more stable than sigma bonds. Sorry, I said that backwards. We have all sigma bonds now, which are more stable than pi bonds. So the other way to think about rate determining step is it's going to be whatever has the biggest leap to get over that activation energy, which will always be the slowest step as well. So slowest step and rate determining step and highest activation energy all mean the same thing. I had it drawn out nicely. Right, so that looks exactly like what I've drawn here.
Yeah.
The draw in pairs. Then that here's what makes our intermediate state. The mechanisms I wrote on the slides fit the other carbon, put a positive charge on, but does that really matter in this case? No. If those two carbons aren't symmetric, then it matters. Just like with elimination reactions, where we put the double bond was based on what else was around it, right? Remember Zaitse's rule? This is today, or this chapter, depending on if we get to it today or not, is when we get to meet Zaitsev's counterpart, the one that he had that feud with. Markovnikov was the one who started figuring out where you're going to put your bromine when you do this reaction. So we have Markovnikov's rule. Then Zaitsev was the younger one. Markovnikov burned in group meeting, and then Zaitsev let him publish stuff that was wrong, and then corrected him in front of everybody else globally, which was a big flex at the time because he didn't just do it in front of everybody, even in his own college. By publishing it, that's now worldwide, even in the 1800s. Because this is less stable than that or that. So it's uphill in energy to make this. So we make a potential energy surface that looks like this. You don't have to draw this to see this, but basically you're going to make something intermediate that's less stable than what you started with. That's going to have a big activation energy because to go uphill in energy, you've got to go over the pass here. Right, so this is like if you're trying to go from Reno to Sacramento going through Tahoe Basin. Right, you're going up over Mount Rose to get to the Tahoe Basin, and then up over Donner to get down to Sacramento. Sacramento's lower in energy at the end, but you got to go through two passes to get there. And the highest activation energy is that first step.
You're making something unstable, it takes a lot of time.
So
To get.
So we can use the drive that you're going to be very familiar with. Go from here to Reno through Carson. From here to Reno, from here to Carson is the biggest step, right? And then from Carson to Reno, you still have to go through a little pass, whatever that has a name now. I forget what it is. But where you're going to spend the most gas is that first pass, right? Because that's the higher one relative to where you started. So if you've got to go through the higher pass, that's going to be, in this context, that means slower. In the driving context, it means more gas. But you see where I'm going with that? And we know that we have to be going through a higher pass because we're making something less stable than what we started. So it has to be an uphill.
But I thought they were going to the north.
They are. So this carbon got more stable because it has a sigma bond instead of a pi bond, but then this carbon doesn't even have a complete valence. So because we make a carbocation, that carbocation is way uphill in it.
It's less stable than this kind of impact.
Exactly. In terms of order of stability, sigma bonds are most stable, then pi bonds, then an incomplete valence. Incomplete valences are at the ceiling level of unstable compared to sigma bonds versus pi bonds. If I was drawing this more to scale, Like, okay, it's downhill in energy a little bit, right? To go from all sigma or all one pi bonds to all sigma bonds versus a giant leap to go from pi bonds to carbocation. Carbocations are going to always be an unstable intermediate. They're almost never stable enough. We can't even isolate them like in a lab. This second step happens so fast that we can't even capture that intermediate.
Like we never.
Under just the right conditions with an exceptionally stable carbocation, might be able to. But you would have to make sure there's absolutely nothing with electrons around. We're talking, so aprotic solvents, got everything just so, maybe.
So that means. That would this everyone takes most energy to like. Break. Is it racing the bottom up or anything?
So the intermediate, the pass, is gonna be breaking the bond. It's gonna be that step that kind of looks like it's in between point A and point B. You're in the middle of breaking this bond, but you haven't formed the new bond yet. So that's gonna be your most unstable state. But if you look at the way that it's curved, we can actually look at this. So again, the analogy that I used, if you went up to the top of Schooner Summit and you put a bowling ball in the middle of the road, is it gonna stay there? No, it's gonna roll one way or the other. Right? Assuming there's nothing else in the way, it would either roll all the way to Carson or it would roll all the way back to Southland, right? It's not gonna stay, and so what makes that a transition state is the fact that it's curved downward like that. And so it's never gonna, that's even harder to capture than carbocation. You literally cannot capture that because it's less than a microsecond. It's an instantaneous transition. They call it a transition state that never pauses there. When you get there, it either goes that way or that way. All right. That was all good review. And then second step was your bromines lone pairs where you draw coming from the charge or attracted to carbon that's positive. And we get our final product. Right, so I'm going to continuously come back to this way of thinking about mechanisms because I think it explains the why a lot more effectively. The way I was taught mechanisms was effectively memorization. Like okay, we're looking at where charges are attracted to other charges, but there was no like why does it go this way versus the other way. This is what makes it make sense to me. So I'm going to keep coming back to this, and hopefully, with some more practice, getting back into the swing of things. This should be a little bit more effective way of thinking about it, rather than just the memorization. I'm sure my professor thought about it this way too, but he didn't that way. All right, so if addition and elimination are the same reaction happening backwards and forwards, how do we know which one's favored? How do we know if it's even going to happen?
Whatever's more stable.
Well, at the end, this is always going to be more stable because it's called sigma bonds. So how can we favor this?
Sterics.
Sterics is one good guess. We have this written at the bottom here as a hint.
Temperature.
So temperature. What is the temperature influence?
Information. Yeah. Well, that's
Going in circles a little bit, but yeah, I'm asking leading questions that way. So This side is always gonna be energetically favored, which means the enthalpy always favors this. Right? Because enthalpy is bond energies. Bond energies are always more stable when it's all signal bonds. I said always, and in general. But the entropy term doesn't care about bond energies. What is entropy based on? Well, temperature affects it, but what is entropy? I guess is what I'm asking.
I had it somewhere.
It would have been, we covered it before midterm last quarter. Think about it more generally. What is, when you first learned entropy back in Gen Chem in probably in 102?
Yeah, like the world.
Close. Entropy is disorder, it's randomness. There you go. So is there more randomness on one side versus the other? Which side is going to have more randomness in a system?
But like global randomness.
So one way you can think about it is if you picked a molecule at random, how many choices do you have if you're looking at the right hand side?
First of what?
How many molecules? If I grabbed my tiny little atomic tweezers and I grab the molecule.
Oh, you could like you choose from 6 molecules.
Yeah, versus 1 in this case, right? If we ignore the solvent molecules, we're just looking at the reaction itself. There's only one product. There's only one molecule here, right? That's not a very random deck of cards. If every deck of cards is the king of diamonds, right?
Yeah.
Versus still not that random, but at least we have 2 options here. We have a 50-50 shot instead of being guaranteed that it's always the same molecule. So entropy favors this one because you get more pieces. You get more possibilities when you have more molecules. So going back, this is maybe a little bit overkill, but just as a better description of what entropy is. Entropy is a constant, Boltzmann's constant, times natural log of W, where W is the number of possible configurations that you have. So like if I'm rolling a 6-sided die, there's 6 configurations that it could land in, right? Yeah, we covered this at some point. You saw it at least. I will never ask you to calculate W because when we're talking about a molecular level, W is huge. But just in terms of like probability, is it more random to roll a 6-sided die or is it more random to flip a coin? 6-sided, there's 6 microstates for a 6-sided die versus only 2 for coins.
Yeah.
Right. So what about if I had 2 6-sided dice? Then there's a lot more possibilities, right? So adding more possibilities means more entropy. And having more molecules means more orientations. Just so you can see where this entropy idea comes from. I'm not actually calculating anything with it.
Oh, double.
Oh, sorry, Ellen's factor. If you go to grad school, specifically in sciences, you will have to take a class called statistical thermodynamics, where you actually will have to calculate some of that. Or if you take PChem in the right school, statistical mechanics is probably an elective in bigger schools for chemistry majors. It's not something that, for chemistry doctorates. Maybe for probably for biochem, probably not for bio. Definitely for any engineering PhD. It's
Like we're gonna need that.
probably not, no. If you transfer, Riley, if you transfer as biochem and you choose to take one of your electives in the upper division as stat mech, then you might see it again. If you stay pure bio, I don't think either of you will. But it's not as bad as it looks. Actually, it's kind of fun when you get the proper scaffolding and you get to learn how to get to run simulations where you actually write the code to have it. Like how many, if I have a 10 by 10 grid and I have 10 particles that I'm going to put somewhere in that 10 by 10 grid, how many microstates do I have? You have to go through that sort of probability, and then you can actually calculate an S value by hand that way. Well, not by hand, but by calculator. As opposed to just general conceptual terms like we're going to stick to here. All right, so in this case, our enthalpy term is going to favor addition or elimination. Which side is going to be favored based on the enthalpy?
Enthalpy favors one, so the
The blue side, yeah. This is our more overall stable molecule in terms of bond energies. And that's what we see.
it favors it because it's more stable.
Because sigma bonds you get better overlap between the orbitals. Sigma bonds in general are more stable than pi bonds. Until you get into benzene rings in aromatics, pi bonds are almost always less stable than sigma bonds. So if you have the opportunity to make sigma bonds at the expense of a pi bond, that's going to be favored by the enthalpy. And just to put a number to it, you can estimate that by just saying, okay, well, I know a carbon-carbon pi bond is about 63 kcal.
So then blue is addition.
This would be the product after addition. You took the addition product and went through elimination, you go back this way.
But you know we don't have from.
No, I'm just putting numbers to it so you have some context. So we can estimate how much the energy it takes to break these bonds is 166 kcals per mole. And then we get this much energy back because we're forming these bonds. So we get 185 kcals per mole back. So it's overall, it's negative 19 kcals per mole. So it's exothermic. Exothermic always means enthalpy favors the product. And if we reverse that, we had to go through an elimination reaction. It's going to be endothermic by the same amount. Okay. Right, because we're talking about that potential energy surface. We're just, if our addition reaction looks like this, in this, that's our negative 19 kcals per mole. Going here back that way, it's going to be positive 19 kcals per mole. Right, so it's the same amount, it's just with the opposite sign to go backwards. And then the entropy term is going to be the opposite. So even though it's always downhill in enthalpy to make the addition products at high temperatures, we're going to favor going back the other way. Because at high temperatures, there's several ways you can think of it, but one of the ways you can think of it is at high temperatures, we're going to favor the side with more pieces. The other way you can think about it is in terms of Le Chatelier's. So remember, Le Chatelier's was basically just like, if you're at equilibrium, If you add something to one side, it's gonna shift the other way to make up for it, right? If this is an exothermic reaction, we're making 19 kcals per mole. If we add more, if we increase the temperature, that's like adding more product. Adding more product is gonna shift it back the other way. All right, let's take a break. Let's come back at 10 after, and then we're gonna get specific about a more complicated version of the same overall product, same overall reaction.
Go upstairs.
What's going on?
Instead of us, this way.
Okay.
And I wanted to like, get like step by step. So I would have looked you.
Yeah,
And I kind of saw it myself, like trying to give the answers and did most like of it. And kind of, I understand. And remember a little bit of what it took to get those answers.
Mhm.
And the ones I have thumbs on are mostly these ones. And so I saw a little bit of your work and I was like, maybe I just was overthinking it, but I wanted to make sure and see like, so, because usually we're talking about next year. Why is it that we, instead of subtracting, but we divided?
well, so we started by subtracting the 32y, right?
Yes.
But to undo this operation, this is negative 9 times x.
Oh.
So to undo a multiplication, we have to divide.
There we go. Yes, so that's where I was getting hung up on. I was like, well,
Yeah.
like I understand why we do this and a little bit of like, but I'm gonna get more clarification on that. And then the same here, this one is just the same here as far as like you want to solve for x, so you want to get the common or the inverse, get that out, right? So.
Yes, we multiply both sides by the y plus 4, and then that means that we don't have anything on bottom here.
Okay,
And then we've got a multiplication, so we'll divide both sides by 1.5, just like we did above,
yeah,
right?
and that's where I got here.
Right.
And then, so is there, what's the difference again for, as opposed to doing this one with the in, or is that the same thing, just doing it?
If it's like doing the butterfly multiplying,
Yeah,
that is doing the same thing.
okay, cool.
Okay, think of that basically, this one.
Yeah.
That's 17 over 1, right?
Yeah.
So if you did the butterfly rule, you'd be multiplying one side by y plus 4 and the other side by 1.
Okay, so yeah, I knew it was something simple that I just wasn't clicking again. And so I was like, all right, I'm gonna do what I can and see what I can get from your work and.
This, if you can do this, like purposely made this a little bit challenging.
Yeah.
So that if you can do this, you can do all the math.
Yeah, and that's what I figured, because I also used that Wolfram Alpha and then we step by step, so that helped a bunch too.
Yeah.
But that's where it only allowed me one step by step, so I was like, damn.
Right, right.
But yeah, and at first I was confused on this, but then I realized like, you're just down as easy as it.
Right, yeah, if everything's multiplication, then all you're doing is multiplying and dividing.
Yeah.
It only gets tricky when you've got multiplication and addition mixed in. Then you have to be careful what order you do it.
Yeah, it's and so.
Right, exactly.
All right, well, that's not as I thought. And I was just like, I knew you did, or actually I didn't. How did we like instead of on another big paper I went and wrote out one word, but is there a more simpler way to do all this?
So you can do it in your calculator.
Okay.
The other thing you can do when you're plugging in your calculator, you just have to be careful that a lot of times with fractions, you don't show it, but it's implied that the top half has parentheses around it.
Okay.
So you have to do this subtraction before you division.
Gotcha.
Otherwise, it's not going to do it the right order.
Yeah.
So if you're, as long as you're careful with that, and then, are you just using your phone as a calculator?
Well, I have a T84, but it's like I gotta go get it. It's at my dad's house. I'm visiting him. So.
Okay. Let me run across and grab it. There's a TI-83 louder here. I'll be right back.
From the last one, though, I think, so I'm gonna try and go to somebody else, but if nobody else, perfect, thank you.
Right, so calculators in your phone calculator will have this something sent to you. You see that yellow E?
Yeah.
That's shortening for scientific notation. So I can write 1.15 times 10 to the parentheses 15. Like that works, right?
Yeah.
What that button does is it gives you that E, which is shorthand for times 10 to the.
Okay.
So you can just do 1.15 E 15 minus 2.5 E 14. And that gives you 9
Okay,
times 10 to the 14. And then you can take that and divide by the other one.
yeah, it's right now, the zero's been.
Yeah, I mean, that'll never let you down, but it's
Yeah.
more than you want sometimes.
Yeah, exactly.
And so the other thing that I'm gonna I'll tell everybody else this too, but I'm gonna harp on it all quarter, is that before you hit enter, you should have an idea of what the answer is. I don't mean like doing all the mental math, but just like, is this gonna be a big number or a small number?
Yeah.
So if you look at this, you're gonna have a big number on top and an even bigger number on bottom, right?
Yeah.
So that means that your answer should be less than 1.
Okay.
If you know that, that'll make sure it catches you, so you don't mess up with your parentheses or something. So if you get your parentheses wrong, you still want type 1 to have something times 10 to the 15.
Yeah.
And you should be like, oh, whoa, what happened there? That should be a red flag, right?
Yeah.
So at least know my answer is bigger than 1, less than 1 is not a bad way to, like, before you even hit enter, know if you're doing something.
Okay.
Something.
Yeah, that makes sense. And then I noticed on the answer key, you had that one at 2.0 times 10 to the 7. And I obviously just round, but how crucial is it gonna be, the dollar?
That's what we're gonna, that's the first thing we're gonna learn is the rules of measuring and rounding.
Okay.
And so, for this one, I'm not gonna mark you down regardless of how many decimals you keep,
Okay,
but I'm gonna teach you that now.
awesome, that's good. Good. Thank you so much.
No problem.
And do you have?
Yeah.
Do you know where I can find T2?
So G are the garden buildings, so, from this.
Are you doing? There we go, down, rolling, hallway. Then turn it right, go down, you go left, that's the T closet. Okay, thank you, run set. Yeah. Yeah. Yeah.
Thanks, Phil.
Hello.
Hey. I think it'll be the third one. And it would just be by one or two. I think one of the people that might have joined, I think he's already transferred actually. He was taking it as elective. And it is kind of a energy intensive elective. And then the other one needs to take the third quarter. So if we see that person, it'll be in the third quarter. But I have not seen him around this campus at all. So it'll probably be the two of you for the rest of the series. So it's a good thing you like each other. All right. Let's talk about a specific type of addition reaction. So I guess before we get into this in detail, we're going to talk about a specific class of addition reactions called hydration reactions. Hydration reactions are addition reactions that very specifically are adding a water molecule. So we have the same molecule we started with on the last one. We're adding water molecule. So kind of what it sounds like. So we're not going to add an H2O in an entire water molecule. Typically, the way this is going to work is what part of the water molecule, we're going to do the same overall mechanism we had before. What part of the water molecule is going to be attracted to hydrogens?
Wait, hydrogen.
The hydrogen's got the partial positive, right? So your first step of a hydration reaction looks the same as with HBr. It's just that we have water acting as the acid instead of HBr acting as the acid. And so we're gonna get the same intermediate. So now we have hydroxide floating around.
It's not a oxygen.
Right, so now instead of adding BR into one side and an H to the other, we're adding hydroxide to one side and an H to the other. So the net result is we added the water molecule, we just did it in two pieces. A hydrogen to one side and an OH to the other. Right, so this reaction can actually go under either acidic or basic conditions. It actually goes faster under acidic conditions because it's easier to do that first step. But under basic conditions, you can do it too, as long as you have something that can give away an H plus. So we typically think of this hydration reaction or this reaction in general as being acid catalyzed addition. You need the first step is you have to put an H plus on one side. So you need something that can act as acid and give up an H plus. So acid catalyzed hydration would just be water with some HCl or some other way to acidify it. Sulfuric acid, I think, actually gets used more than anything else. The problem with this, if you want to call it a problem, is that it goes through that carbocation intermediate, right? Carbocation intermediate opens this up to what other wrinkle? Rearrangement. So this next type of hydration reaction, this net result is still, if you look at the reactants in the final product here, it's still, we broke a pi bond and we added an OH. So it's still a hydration reaction, but it's going to go through a mechanism that doesn't have a carbocation.
The oxymercuration.
Oxymercuration followed by demercuration. So it's the two steps. Oxymercuration is this step where you get this mercury with an acetate attached to it. And then the demercuration is basically just reducing the mercury and takes it out of the system. You get metallic mercury as byproduct. But if your product we actually care about is the alcohol. All right, and so this is going to be the first mechanism that's going to be a little bit of a wild ride. It's going to feel a little bit. The other ones, even if you wouldn't have come up with them on their own, they all made sense, right? This is going to be the first one where you're like, whoa, what just happened? Let me get my coffee ready first. This is all one. Well, so this is mercury 2 acetate.
Okay.
Has this structure. Mercury 2 acetate. That mercury, the reason that we see this a lot with metals, especially D-block metals, get used a lot in OChem as sort of catalysts or as reactants because they can have a variable number of bonds pretty easily because they have multiple possible oxidation states and they have those d orbitals. They can accommodate a lot of electrons or very few electrons. So the first thing that happens here, let me see if I don't have the arrows strong. Good, I'll do it myself. Is basically this mercury has a lone pair on it. But effectively what happens is one of the acetate groups gets kicked off. You wind up with this sort of weird exchange transfer, where the mercury gives a pair of electrons to the carbon. But then the pi bond gives electrons to the mercury at the same time. And the reason that happens, and actually this here, not that. The reason that it can do that is because these D block metals, especially stuff like mercury, they're really, really large. So even though normally we don't make something that looks like this, where we get like a three-sided ring. Three-sided rings have a lot of strain energy, we would say normally, right? Except that in this case, because it's a mercury, it's so large that it can kind of be all over the place. It's kind of in two places at once. So we get this three-sided ring as an intermediate. It's going to very quickly. So that's the second step, is once you get this three-sided ring, it does have some strain energy. But if you have the carbons still have partial positives. And so the carbons are still an attractive target for a nucleophile. So the second step is just going to be a nucleophilic attack. If the other purple had more weak in it. And the oxygen is going to attack the more substituted carbon. Kind of. Zeta Central says you make the most substituted alkene. We're breaking apart an alkene. So this is more about carbocation stability. The transition state for attacking this carbon is a little bit lower in energy because the transition state kind of looks like a carbocation. You can also think of it in terms of sterics. Mercury is really, really big. So mercury is going to be closer to the empty side than the side that's got more stuff around it. So it's not an isosceles triangle. It's not equal, these two bond lengths. The bond between the mercury and the more substituted carbon is a little bit longer.
And so what about the more substituted?
That's going to be where the oxygen attacks. The oxygen is going to act as a nucleophile and attack the more substituted carbon. And that's what's going to give us our intermediate. Mostly. We did then just do a proton transfer to get rid of one of the protons on water.
Okay.
So we'll actually get an intermediate that looks like.
It's a proton transfer, one of the four. Yes.
Yeah.
It's for the attack.
Nucleophilic attack, proton transfer, rearrangement, and leaving group leaves. So this is kind of a combination of nucleophilic attack and leaving group leaves. It's like an SN2. Basically, the mercury is leaving from the more substituted carbon at the same time as the oxygen is coming in. And that's what stops any rearrangement. It can't go through a rearrangement because you never get a full-on carbo. You get an SN2 on the more substituted carbon. And then your proton transfer step, whatever you have, you can use the acetate that we kicked off here. That acetate that left, still floating around, that's a good base. Well, if you look at what we got here, basically we replaced one of these acetate groups with our carbon, with our alkene. So I missed it when I first drew it. All that's the step that's less important than making the three-sided intermediate. And then you just have, if this is now the intermediate, after our water attaches, we just need something that can act as a base. Take that extra H+. So we did that we did that at the end of last quarter, right? We had some like cleanup on some of our E1s and SN1s. Where after we added the water molecule, we had to do a proton transfer. Alright, so this is these two steps are the key steps. Because this last step, we're not gonna go through the mechanism for it, it's beyond what we're gonna cover in this class.
Okay.
We're basically just gonna say, once we get to our oxymercurated intermediate, we just add a reducing agent. And our most common reducing agent that we use in this class is gonna be sodium borohydride.
Sodium oral.
Boro, like boron. Sodium borohydride basically is just a way, it's just gonna basically take this mercury and turn it all the way to metallic mercury and pulls it out of everything else. So we're gonna get metallic mercury. And we're gonna replace mercury on both of these with an H.
On where?
So this intermediate that has the mercury attached to our starting material and then has its other acetate group that's still hanging around. The sodium borohydride. Basically, we're gonna spend more time with this later, but one of the steps is gonna be that these hydrides, hydrogens, this is a useful reducing agent because the hydrogen is the most electronegative thing here. Which usually that's not the case, right? So hydrogen is the most electronegative thing here, it's actually got a partial negative. This is a way to make hydrogen a nucleophile. Because you basically just get a H minus instead of an H plus. And that basically just does that and kicks off the mercury. Like I said, there's other steps that go along this as well to get us all the way to our final product. But a reducing agent, the other name for this is called, they call it a hydride source, because it's just a way of having extra, H minuses. They can now come in, and the hydrogen acting as a nucleophile is kind of useful sometimes when we just want to make a new carbon hydrogen bond. Alright, so the net result though of the second step, second part is what's most important, which is we cleaned off the mercury, we get metallic mercury. And our starting material is now turned into an alcohol. With no rearrangement possible. Right, and it's gonna add the oxygen in the more substituted spot. That's Markovnikov's rule. Markovnikov's rule is that when you do an addition reaction, your nucleophile usually attaches to the more substituted part.
Right.
It's the worst one so far. Don't worry, it gets worse. Alright, so really the new piece here is that we added mercury.
Yeah.
And we made this three-sided ring as the intermediate.
Mhm.
No, once you've come this far, there's no turning back. So AC is just shorthand. This is an acetate polyatomic ion, right? So the same way that we use it for methyl or ET for ethyl, AC or OAC means acetate.
So AC or OAC? What are you going to use?
OAC.
now and then I'll call it. I don't really know what's happening, but I'm ready to. I don't think I can get that on my own pay yet, like it's.
Starting to get it.
Yeah.
So, and this is why the mechanisms are worth more points and there's fewer of them. Because at the very least, if you go into the midterm knowing, oh, I see mercury with 2 acetates and an alkene. So the way that, I think on the next slide.
I know.
This is the way we would write it as reaction.
Same thing with the.
It's the same thing. Mercury with 2 acetators attached, and then water.
That's the same as the slide before.
Yep. This is just showing the intermediates. It's an alkene,
But it's-
mercury with 2 acetates, and then water is an nucleophile. Sorry, this
Oh,
is the same net reaction, starting with a different color. Right,
so these
sorry.
are steps mapped.
Yeah, it's just new reactions. Now still have substitution and elimination. But now we also have some addition reactions. We have the acid catalyzed addition, which was the simple one we started with. And now, but the problem with just using acid catalyzed addition is that it can rearrange, again, that's the products, and it's not very effective. Oxymercuration, it's less ideal in some instances because we're using mercury, which is toxic. We try to avoid that. But at the same time, it doesn't allow any rearrangement and gets better yields actually. That's a good question. Thought about it that way. We think of elimination as subtraction. And we think there are some reactions that you could call multiplication. Maybe we could think about it that way. Careful what you wish for.
I mean,
All right, so but the main thing is that this is your key. If I'm not asking you to draw the entire mechanism, all you have to know is this is gonna be hydration. And it's gonna put the OH on the more substituted carbon.
are we gonna do this?
Yeah. And while you're doing these ones, give it a try. Take a second. I'm gonna go see if I can find some new markers real quick.
What are we doing? We're just gonna be making the backs. We're just making the product. What? We're just doing the product. Why are we doing all of this? All because it has 2 steps. Remember, we still not much talk. Is what happens. Track and then the one on bottom is what we must, until he does stage. So, but how do we apply it to the right to the silver? This worked out. So we just need to know what the color is. You just hold still for a second. You're like, do you know? Let's go. Like we need to figure out how to get But that's not gonna be our, you gotta start with the circle. Well, it's not gonna be exactly this measure, we gotta figure out how we make something that's like this turn this. You just don't want to understand first. Or we can do this first. Do you want to draw out like the whole reaction? It's out. Well, we start with the HG and the hydrogen trade-off in this here. But what is this the cycle? What this is what it looks like is what we start. This is one. So this is gonna be this. It's what? I wonder if you ever watched back the video of this classroom. Doesn't do this often.
All right, got the good stuff, the expos. All right,
You know, like which carbon is gonna get it's the most substitute.
bingo. So you do get it, Taylor.
But I don't know how to go from this to any. And
Okay, so the net result for this is, sure,
all together.
yeah.
Great.
So,
So from, I know the first step is that the HG and the carbon is switch off.
right, so basically, mercury has a lone, this is why mercury is so useful for this, why we use it even though it's toxic, is because it's relatively stable and has a lone pair, but it's not more electronegative carbon. So it's gonna make it easy to use this and get rid of it at the end. So what happens, lone pair attaches to one side. And the pi bond attaches to the mercury at the same time. And as a result of all of that going on, an acetate group leaves.
And what you just proved, the. That's.
These are intermediate. Well, all those medications you're gonna need to be prescribing, dosing, are all made using these reactions. And if you understand how these mechanisms work, then that'll help you understand how the mechanisms in the body work. This is basically setting you up so that when you get to biochem, the mechanisms aren't completely foreign. You know what a mechanism is. But if you just jumped in and started with a protein catalyzed mechanism, you'd really be lost.
From here, we reduce it.
Not yet. Because we still have that, we still need water to act as a liquid file.
Okay.
And it goes to the more substituted carbon. So the process. Sorry, what where? Mercury with 3 bonds to plus, so the mercury takes the extra electrons.
The bond that goes and in the mercury is right on the bottom.
Because this bond is electrons, right?
Yeah.
So mercury goes from having 3 bonds, only having 2 bonds, so now has now it's neutral. And it still has one period.
Oh, the long term.
Because it turned into, hey, don't think too hard about tracking lone pairs from mercury because it's got a d orbital and its lone pairs are weird. In my opinion, I think it actually has another lone pair as well, but that's not. The point is that we get to this intermediate. Yeah. And then water can attack any nucleophile at this point, really. It's gonna attack the more substituted part. More carbons attached, more things around. And then we get to this step, and then it's a quick proton transfer to clean it up. So you can use that extra. We didn't show it, but when we kicked off this acetate group, there was a plus. An acetate now floating around, right? So since we have an acetate floating around, might as well use that as our base. That's the first half, right?
That's half.
That gets us to the end of step 1. So this, when we write reactions like this, it's saying the first step of this. This gets us to the end of the first step. Luckily, the second half, we're gonna hand wave a little bit. We're not gonna do all of the mechanism steps for the second part. Because there's too much going on. The second step is you add your sodium borohydride. And all we're gonna say for that is, it's just gonna clear this off.
The HTOAC.
HGOAC is gone. So our final organic product. Alright, so we're getting to the point in these mechanisms where you're not going to want to draw all these steps out for every one of these reactions on the midterm, right? So it's going to be really helpful to, one, you need to know this on some level, but when it comes to answering this question or defining a situation, knowing that all I'm really going to be doing is take away a double bond and put an OH on the more substituting carbon. That's the net result. So final answer for this one, all we really need to do on, if it's a reaction problem on the test, is right there.
But it's like,
If I said show the mechanism, I want the whole thing.
anything. How does that apply to other? Is it always gonna be an OH that you add to the most?
As long as you're using water as your nucleophile. But that's exactly gonna be the next thing I was gonna put on here is, what if it's methanol? If it's methanol, you don't add an OH, you add a methoxy group. You add an oxygen and another methyl. If you add ethanol right here, then you're gonna add an ethyl group instead of an H. But we'll get there in a second. For now, as long as it's water, it's just an OH.
If you're saying added on the most sensitive carbon, but there is. Yeah, it's wrong.
In any case, really, if it's an alkene, there's only two sides to the alkene, right? Yes. So, no. And the second part of this question, what if it was catalyzed hydration instead of oxygen hydration? Then you need to worry about rearrangements. Because acid catalyzed, the first step is going to be you break the double bond and make a carbocation, right? And that's an easier mechanism to show. That's the mechanism we started with, where we had an acid, like HBr. We started talking about where are all the extra electrons, where's the electron density? It's in the pi bond, right?
Right, those are the extra.
Yeah. So this is the one that's reversible. The other reason this is useful, this reaction doesn't happen back.
Okay.
So it's irreversible. The first one we talked about, we're talking about enthalpy and entropy. That's an equilibrium reaction where it can happen back both directions. So first step here, if it's acid catalyzed, is when we break that pi bond, we have to choose where to put the positive charge. Where is the more stable place to put a positive charge? Where's the more stable carbocation? On the more substituted. So your intermediate then looks like this.
But.
There is no hydrogen there, so it's the other one. The whole methyl moves over.
Okay, I didn't know that was possible.
Those are the only two things we see migrate regularly. It's either going to be a hydrate migration, where a hydrogen brings its electrons over, or it's a methyl migration, where it's a CH3 that brings its electrons over. So basically, we're going to see that as our mechanism step. So now our methyl moved over, our positive charge is there. So your net result in this case is going to put the OH group on this carbon. Remember, the second step of these acid catalyzed hydration is the water donates a lone pair, the carbocation. Then a quick proton transfer, we get an alcohol again, but on this carbon instead of that carbon. So acid catalyzed is a simpler mechanism, but it can give you a more complicated system overall. So if we wanted to rearrange, if this is the product we're trying to make, we would do acid catalyzed. if we wanted to make the product without rearrangement, we have to use oxymercuration. If we wanted to make this molecule for pharmaceutical purposes or anything else, we have to go that route. Take your time. This will be the last slide that we do today.
Wait, where did this?
Okay, so this is the product of first, and then the second part of the problem is what if it was catalyzed hydration? That's the right half here.
So the first one we did was the oxygen mercury,
Good.
right?
Yep. They're both hydration reactions. They're both Markov-Makov hydration reactions, where we put it on for substituted carbon. But one allows rearrangements, the other one does not. Okay. The probably meeting once a week with no labs. Feel like we're just getting started. So last thing for the day.
Yes.
What do we get here?
Okay. No double bond and the OH on the second. Well, how do we mix with the? But I thought it on the oxy for the acid.
So it would drive something like, or draw over here. So it would be all one step, and we would just say H2SO4 in water. H2SO4 gives you the acid to start the process, and water is the file that you're gonna add. So that would be the short, the way we write acid catalyzed hydration. In this case, you just need an acid that's not going to react to give you that H plus to start the process. Sulfuric acid gets really commonly used because we don't want to use hydrochloric acid because then the chloride acts as a nucleophile and interferes with the process. We get side reactions. So for an acid pad, and sometimes we just have it written as just H3O plus because that's just an acid in water. Or sometimes you might see it written as H2O and acid. This is probably the most common way because that's the actual conditions. Yeah, you do it in water and you add a couple drops of H2SO4 to start the process.
So if we wanted to add analyze for that, we would.
Well, let's sketch the and write the product for oxymercuration.
No, I got about, what was the arrow?
That will be the way that we write acid. So this is the way we write oxymercuration. And then, so our product would then be this. If we wanted, if we do the same molecule, and we want to say acid catalyzed hydration, it would be H2SO4, H2O, or even H2O plus, and then just H2SO4 as a catalyst over the arrow.
instead of that.
instead of this. If it was acid catalyzed, we get an intermediate.
So. Then it's gonna go very, but then two first.
Right.
So, does it have H2SO4 and the H2O or?
Yes. You need the H2SO4 at least a few drops of it to start the process. But then the water is the actual reactant.
It's not too bad, but you know how to shortcut it.
Right, we added 2 new mechanisms today, but one made sense.
Yeah.
It's just the opposite of elimination, so it's similar to what we've seen before. This one's a tricky mechanism, but when you know the shorthand, it's not too hard to write the problems.
You don't
Yeah, we
visualize it.
the trick with doing this one, just as the shorthand, is you have to watch out for rearrangements.
Yeah.
So you have to write the intermediate in this case.
What if I could see that that's where you're going?
Then if you just wrote this as your answer, that'd be full credit. If I just said, what's the problem? If I say, what's the mechanism, you gotta show all the steps.
Okay. Yes, I want to see.
You wanna do a quiz with some practice for these two? Like basically I'm gonna just do this same slide, just with some different starting materials. And then maybe one where you have to write the mechanism out for practice with that, for the oxymercuration. Okay, yeah, I'll set that up. It's not gonna go live till later, because I still have to prep a lecture for the high school. But sometime tonight or tomorrow morning, I'll have the quiz will be ready. You want me to set up an announcement, or you just check it on Sunday? Just
Need some extra practice this first piece.
Yeah,